In this short presentation, I'm going to briefly describe the development of an integrated approach to testing and assessment for grouping nanomaterials to estimate their thermal absorption within the GRACIOS framework. The GRACIOS framework aims to enable the practical application of grouping, leading to read-across and classification of nanoforms in order to streamline the risk assessment process. Grouping decisions will be underpinned by scientifically justified hypotheses, which identify descriptors relevant to grouping of similar nanoforms for a specific endpoint. Within the GRACIOS project, we have developed a number of predefined hypotheses for grouping and read-across. Based on the basic information inputted into the framework, a predefined hypothesis may be suggested as suitable for grouping the nanoform under investigation. Each predefined hypothesis is supported by a tailored integrated approach to testing and assessment that will guide the gathering of relevant information, allowing the applicability of a grouping hypothesis to be assessed. The IATA ensures that testing is conducted in a targeted manner that allows integration of existing information with new data generated when necessary, supporting the user in accepting or rejecting the grouping hypothesis. Here I will briefly introduce one of the GRACIOS predefined hypotheses that focuses on grouping nanoforms based on their potential to penetrate skin in their particulate form. Keeping in mind this main aim, the hypothesis focuses on intentional consumer applications and occupational exposure, which can result in high dermal exposure situations. Although dermal penetration of nanoforms has often been concluded to be negligible, several studies have shown that nanomaterials penetrate into viable layers of the skin to some extent. Such low degree of dermal penetration of nanoforms is thought to be plausible mainly via the intercellular route through the lipid matrix around the keratinocytes and through skin appendages like hair follicles, sweat glands, and pores. The hypothesis is based on considering that primary particle size is a limiting factor in dermal penetration of nanoforms. We recognize that there are several other nanoform properties that can affect absorption, such as agglomeration or aggregation, and surface charge and hydrophobicity. However, agglomeration and aggregation are rarely reported in scientific publications evaluating dermal absorption, and conflicting conclusions on the effects of surface properties exist. Besides such particle-related properties, the choice of the formulation used to apply the nanoform on the skin and the skin conditions are also major determinants of skin absorption. This hypothesis can be used to evaluate if nanoform fits in a predefined group. In this case, whether the worst-case dermal penetration factor is applicable, or to support read-across for dermal absorption, local and systemic toxicity after dermal exposure from a source material. I will start describing the hypothesis for the predefined group. Within what they are, we define criteria that determine the applicability of the hypothesis, in particular, an exclusion of nanoforms that are flexible or that can change their structural conformation, and a size threshold of 5 nanometers. Note that this 5 nanometer is used as it reflects the boundaries of the dataset that was used to derive the worst-case dermal penetration value. Meeting the characteristics defined on what they are determines where they go, in particular to which extent the nanoform could penetrate healthy skin up to viable layers or systemic circulation. 1% of the external dose is used as a worst-case dermal penetration value based on existing data. Furthermore, what they are and where they go together address their potential to induce particle-specific toxicity by the dermal route of exposure. Besides concluding on whether a nanoform fits into this predefined group, the hypothesis also can be used to support read-across. Within what they are, we include criteria that define the applicability of the hypothesis, and also physical and chemical properties that need to be sufficiently similar between the target and the source nanoforms in order to support read-across for dermal penetration in their particulate form. These conditions in what they are will determine where they go. In this case, the extent of thermal penetration and absorption into systemic circulation, and what they do. In this case, the type and extent of particle-specific toxicity that can be expected. concluding that a target nanoform is sufficiently similar to a source in this hypothesis, which focuses on particles, and in a complementary one that focuses on dissolved chemicals from particles, allows to read across for local and systemic toxicity after dermal exposure. Whether a nanoform or a set of nanoforms belong to the predefined group in this hypothesis or can be compared to a source material can be tested by a tailored IATA. This takes the form of a decision tree, where each decision node asks for specific information related to the key criteria required for assessing their potential to penetrate healthy skin. Each decision node is measurable with defined criteria to ensure a clear yes or no answer. For example, whether a nanoform dissolves sufficiently slowly to consider particle-specific effects. A yes answer allows progression through the IATA, whereas a no represents a point of departure where your nanoform may deviate from, and therefore you may reject the grouping hypothesis. Rejection of the grouping hypothesis may prompt the user to consider an alternative hypothesis. For example, quick dissolution may lead you to consider hypotheses related to grouping due to similar toxic ion release. As introduced before, this hypothesis can also be used to support comparison of a target versus a source nanoform. And for this, additional decision nodes need to be considered. In cases where no relevant source material is sufficiently similar, concluding that the nanoform fits into the predefined group will at least allow using the worst-case thermal penetration factor. The decision nodes may be addressed by a single descriptor, such as constituent particle size, or a combination of descriptors, such as surface properties. They may also be higher-tier assays that simultaneously address several decision nodes, such as in vitro dermal absorption studies, which would be an alternative to these predictive decision nodes. The information required to progress along the IATA can be gathered at different tiers of testing, from simple cellular characterization and in vitro screening assays to more complex in vitro models, such as in vitro dermal absorption studies, and finally in vivo models, including OECD test guidelines. This tier approach from simple to complex testing can be used to support a grouping decision with increasing levels of confidence. The choice of tier at which you exit the IATA will depend on the initial purpose of grouping and the associated level of uncertainty considered acceptable for the user needs. Therefore, the tier testing will reflect the level of confidence you require in the substantiation of your grouping hypothesis. We propose a number of purposes for which the use of the dermal penetration hypothesis and IATA will be appropriate, and highlight some of the potential implications resulting from grouping for each of these purposes. The hypothesis may facilitate the generation of a read-across argument for risk assessment by enabling the selection of an appropriate source material. Read-across to the source material for which more information is available for the endpoint of interest may allow waiving of testing. This hypothesis may, in safe-by design context, be used, depending on the exposure scenario, to conclude on minimal dermal penetration, waiving concerns on dermal exposure, or to inform nanoform design in order to minimize thermal absorption, and or by identifying upfront a potential source nanoform for read-across, which would minimize needs for thermal toxicity testing. Finally, this IATA may be used to fill data gaps and increase scientific understanding of key properties determining dermal absorption of nanoforms. This may lead to a refinement of the boundaries of the group, thereby further streamlining the risk assessment process in the future. Here I have demonstrated the practical application of a gracious IATA supporting an evidence-based grouping hypothesis for dermal penetration. This example illustrates how the mechanistic links between the phys-chem characteristics such as size and functional properties such as hydrophobicity can be integrated to form a well-substantiated grouping hypothesis. For further information on the gracious framework and examples on the gracious IATAs, please see our additional video presentations. Thank you.